As an example of where participating media are important, I want to consider the greenhouse effect in the Earth's atmosphere. So I'll start by considering the total amount of radiation given by the Sun, which is just given by the surface area of the Sun times sigma T to the fourth. I'm treating the Sun as a black body with an effective temperature of 5778 Kelvin. Then the energy per unit area received at the average orbit of the Earth. I have to say the average orbit of the Earth because of course the Earth's orbit is actually elliptical. We're going to effectively treat it as a circle with some average radius capital RE. Then that average value is simply given by 4 pi rs squared sigma T to the fourth divided by 4 pi RE squared. This term is obviously actually the surface area of a sphere with a radius capital RE, but the radiation from the Sun will have spread out over the surface of a sphere, so I have to actually divide by a spherical surface, not a circular one. Obviously the 4 pi terms here are going to cancel out, and I simply end up with sigma T to the fourth Rs over Re all squared. The lowercase indicating I'm dealing with the radius of the Sun, the capital being the orbital radius of the Earth, treating the orbit as a circle. So plugging in appropriate numbers into this equation, what I get for overall for the energy per unit area received at the average orbit of the Earth is 1366 watts per meter squared. The actual radiation intercepted by the Earth will be given by the Earth viewed as effectively as a circle in first instance, because it will be a circular area that you see from the Sun, and that will simply be given by pi times lowercase re squared. Actual energy is then averaged over the actual surface area of the Earth, which is going to be of course 4 pi Re squared. Looking at this equation, the pi Re squared terms will cancel out, and we simply get 1366 divided by 4 equals 342 watts per meter squared. Now the Earth is reflective. The reflectivity is 16% if we ignore the clouds, it is 33% if we include the clouds, and that's assuming all other radiation is actually absorbed. So if I now assume that the Earth emits as a black body, we can work out the average temperature of the Earth by considering that the fact that this is the total radiation received per unit area from the Sun, times 1 minus the reflectivity, so this R is the reflectivity, times the effective surface area that is receiving this radiation, which is pi Re squared, and then that must be balanced if the system is in thermal equilibrium by the emitted amount, which will be given by the total surface area of the Earth, because it is a sphere, times the Stefan-Boltzmann constant times the temperature of the Earth to the power of 4, i.e. we're treating it as a black body, as I've already said. Rearranging that slightly, we can say that the temperature of the Earth will therefore be given by S times 1 minus R divided by 4 sigma, all raised to a power of a quarter. So if we do that for the reflectivity of 0.16, i.e. the case of when we have no clouds, we end up with a temperature of -6 centigrade. If we actually do it for when we have a reflectivity of 0.33, i.e. when we do have clouds, we end up with a temperature of -21 degrees centigrade. Clearly these temperatures are much lower than the average global temperature. And in fact, if those values were right, the reflectivity values would have been wrong, and this really points to how important the greenhouse gases in the upper atmosphere are in terms of preventing the Earth's temperature being as low as those previous calculations would indicate that they are, because clearly if they were that low, then essentially we would not be here. So greenhouse effect is real and important, because the greenhouse gases act as a radiation blanket. They absorb radiation from the Earth in a relatively warmer region, but they emit to space from the upper colder region, and the overall thermal balance that this gives us helps achieve a warmer temperature on the Earth than we would otherwise expect. So if we make use of the Wien displacement law, which is an observed feature of thermal radiation, namely that the wavelength times the temperature, which gives the maximum power for any particular temperature. This is the wavelength at which there is maximum emission, essentially, for a given temperature. The product of those two terms is always 2897.8 micrometers Kelvin. So for the Sun at 5778 Kelvin, that means that the maximum power occurs at 500 nanometers, in other words, in the middle of the visible spectrum. Whereas for the Earth at an average 298 Kelvin, then the wavelength at which there was maximum power will be 9.7 microns. So this is really the peak of the radiation spectrum. From the Sun, it's peaked in the middle of the visible spectrum. From the Earth, it's actually peaked into the infrared. And the overall energy balance, taking into account all these effects, turns out to give us an average global temperature of about 15 degrees centigrade. The actual balance, of course, has to take into account both the incoming radiation from the Sun, reflection from the clouds, atmosphere and the surface, the emission from the surface, the emission from the clouds, and the emission from the greenhouse gases. And also, in terms of the overall energy balance in the atmosphere, convection is important in transferring heat around the globe. But when you go through those calculations in detail, you get a global average temperature of about 15 centigrade, which is clearly significantly higher than the global average temperature that you would calculate based on a simple energy balance with no greenhouse gases. So the participating media, their absorption and re-emission is very important in determining the overall average temperature of the Earth. And of course, this gives us a problem now that we are putting significantly more greenhouse gases into the atmosphere. And if you go to looking at the parts per million CO2, this is measured at the Mauna Loa Observatory on Hawaii. You can see there is a clear and very steady increase in the atmospheric CO2 measured at that observatory. There is variation during the year, but the overall trend around that variation is for a very, very clear increase, and this is data released in November 2016. In addition, we can attempt to measure the global temperature. The averaging that goes into this is relatively complex, obviously. This graph shows the difference from the 1961 to 1990 average over the period 1850 to 2000. So clearly this is the region where we're looking at the difference from. Prior to that period, the difference tends to be negative, i.e. the temperatures tend to be lower. Since that period, the temperatures are clearly going up really quite rapidly, and essentially we are seeing global warming, and a significant component of this is due to the release of CO2 by humankind into the atmosphere, so that the CO2 levels in the atmosphere are now significantly higher than they were in the pre-industrial era. Of course, some people will try and say that this is all a completely natural effect, and there are natural variations of CO2 in the atmosphere over the very long time scale, but the very rapid changes seen really since we first industrialized about 200 years ago are producing significant changes in the atmosphere and significant changes in global temperatures. So therefore, to summarize what I've covered today, I've gone briefly through radiation shields and the fact that thin metal foils with very low emissivities are what you want to act as radiation shields. I've then looked at participating media, briefly in terms of some of the complexities that you would have to take into account if you're really going to try and analyse for that. And then to show how important it is, I've looked at the greenhouse effect, which is actually essential for keeping the Earth at a habitable temperature, but also then drawn attention to the fact that we are now putting in additional man-made greenhouse gases which are leading to temperature anomalies and changes to the long-term global climate. Thank you.